We'll be talking about the simulation, prototyping, testing in aerospace and defense sector with the latest developments. So what we normally do is replacing the physical prototype, doing various kinds of simulations, and then how to handle the manufacturability aspect, prototyping aspect, and then the virtual reality aspect of the entire manufacturing process. So if you see initially physical prototyping or probably the simulation was used only to conduct designs as a checklist. And then at later point of time it moved into replacing test. When you talk about replacing test, it is talking about individual single parts that could be tested on the simulation basis and then going into the manufacturing. But later it was actually evolved into a replacing of prototypes, which means you could build the entire car assembly, including various manufacturing process that is coming associated with the manufacturing itself, and then replacing the complete prototypes so that you could actually do everything virtually. Now it is getting evolved into making smart prototypes, which is probably associated also with Industry 4.0, where every vehicle is interconnected with the other, and we would want to know what is the influence or what is the prototype that you could actually simulate it smartly to interact with the other vehicle designs, etc. When we talk about the global competitiveness of GMCI, which is Global Manufacturing Competitive Index by 2020, it predicted that there are 15 countries which getting into the manufacturing mode, and then which is actually getting into the competitive edge of manufacturing, and India stands at number 5. So it's a very big market for India to develop, and then we are there working along with the industries to see how we can actually take the prototyping to the next level and then replace the virtual prototyping and testing, etc. When we talk about manufacturing, virtual manufacturing enables and then is building with materials, especially the future materials, which means you're working on very complex materials, very advanced materials. And then when we talk about especially the aerospace sectors and then the other defense sectors, we are even having more challenging materials in terms of composites, in terms of aluminum, in terms of titanium. So we have to address all these various aspects of materials, and then it requires different manufacturing processes as well. So why virtual testing is required? Because if you see a full aircraft or something which is associated with defense sectors, it's not possible to actually get into the physical testing or real-time testing. So we will have to rely on the virtual testing, and then the predictive method is basically to predict the quality and then function to eliminate defects or probably various kinds of problems that arises during the manufacturing aspect, to reduce the cost and then minimize the lead time. So these are the main reasons why we basically have to get into the predictive maintenance method and then the virtual testing method. So ESI as a company offers many manufacturing solutions associated to processes. One is composite manufacturing solution, the metal forming solution, welding and heat treatment, casting solutions, which includes various types of gravity tie casting or HPDC, LPDC, or various other casting process, including the virtual reality solution, where you can do a design review and human-centric approach with respect to the casting, with respect to the design review solutions, and also the additive manufacturing solution for metals. So these are the range of manufacturing solution that we offer as a physical prototyping. So let me get into the details of every manufacturing process and then every manufacturing process possible in ESI. So first one is getting a creative and attractive lightweighting for energy efficient aircraft. So first one is basically the composites. So when you talk about the composite manufacturing process, it includes three interlinked process. One is the pre-forming of the part, the infusion, which is the RTM process, and then understanding the distortion because of the residual stresses coming due to the infusion or due to the curing or the curing process itself. So when we talk about simulations is garbage in, garbage out. So basically you'll have to have the correct material parameters, which is the basic of any of this testing itself. So there are various ways of actually understanding and then creating the material characterization when you talk about the composites, because composites as such is not something which is a ready-made material available, but you could build your layers and you could build your composite stack sequence, etc. So you basically can influence your particular stack of material, and of course you can test your material based on the stack of sequence that you are trying to create. One such test is the picture frame test and then the cantilever beam test to understand the material mechanical behavior of the material. And of course for doing the resin transfer molding, you need the viscosity of the resin, kinematic enthalpy of the resin, specific heat of the resin, etc., including the fiber density and then the permeability information. So you get all this information starting from the test of the material, which actually acts as a major fuel for doing the simulation aspect as such. When we talk about different formability, different forming simulations in PAM composites, first one is the pre-forming or the pre-pack forming. It could be for dry fabrics or it could be for the pre-impregnated fabrics, where we do the pre-form simulations, and we would be able to characterize and then determine the kinematics of the tool, the temperature cycle, the pressure cycle, the clamping conditions, clamping forces, and then the pressure on the mold, the strains that is coming on the shearing fibers, the shear itself of the fibers, etc. So once we have the preform ready, we would be able to directly take it to the autoclave and then do distortion analysis, or you could take it to the RTM process and then do various kinds of RTM process like RTM or vary or light RTM process, SERTM process, HPRTM process, to see what is the best way of injections, location of injection gates, location of vents, and then position on the size of the flow, and if you want to adapt to a heated mold or something like that. So which will automatically predict you the air entrapments or the microporosities, injection time, temperature evolution, etc. These are some of the things that we would be able to simulate, which will reduce the physical prototypes as such, and then by the end of it you can also do a curing cycle analysis, with which you will be able to understand the distortion itself. So let me get into some case studies, what is possible, or what are the things that I was talking about in PAM composite. Basically, this is a six-layered woven fabric material, where they were trying to do a preform analysis, and then they were trying to understand what is the wrinkles that is coming on the component, what was the bridging effect, and then and what are the process parameters that need to be modified to get a part which is actually not say completely wrinkle free, but a possible part which can be taken for further analysis. So in this they were actually trying to do this complete simulation, and then they were able to see the shearing effects that is coming on the woven fabrics, and then the bridging, and then the gaps that comes in between each fibers, and also the thickness variation detection were diagnosed, which was very much with respect to the reality. One such also example of 20-layer UD ply carbon fabric for a part where they were having the thermoforming of this part, where they have a 20-layer sequence, and then the first layer or the top layer was wrinkle free, but there was huge wrinkles that was coming from the bottom layer, the 20th layer. So they wanted to actually replicate this process and then optimize the process by using different blank holder force conditions, different velocity, tool velocity, etc. And they were able to successfully identify the defects as well as cure also rectify the defects. One such also tool was basically the flat pattern, or the outline of the blank that probably have to be used to reduce the amount of defect or the poor quality that is coming out. So we were initially able to successfully simulate the 4 plies flat pattern, and then we understood that there is large amount of wrinkles that is coming on the component, and then the optimization solver was launched behind, and then it was able to give us an optimized output flat pattern, which were used for a defect-free component manufacturing. One also example of an airbus is basically to understand the shearing behavior and then the wrinkling behavior on the prefabric part. It's again what you could see here is the impact of shearing on the injection process and then the product performance. The whole of the exercise was done to better understand the influence of parameters like various parameters, and then also the generation of wrinkles and shear observed on the preform. A real-time example again with one of the aceturi, where the whole of this process was conducted to first understand the manufacturing behavior and also to create a robust manufacturing method for this section frame. What you could see here, this is a very interesting complete chain process, where they initially did the heating and then they actually did the vacuum forming. After doing the vacuum forming, they took it to the injection process, resin injection process. They did the RTM process, and then finally they understood what is the distortion that is coming on the part. When they understood that the amount of distortion was outside the tolerance limit, they went back into the preform. They changed the mold of the preform and basically adapted the preform so that finally, when after the distortion, the component was within the tolerance range. So the whole of this process simulated chain link was possible because we will be able to do the entire chaining process itself, like preforming, RTM process, and then the distortion associated, along with the compensation or the preforming compensation that could be done along with that. I move into the next solution, which is the metal forming solution. We have various aluminum and titanium materials that is basically formed using the metal forming process. If you see, there are many challenges that is associated with aluminum material with respect to titanium material, with respect to high tensile material, high strength steel, and basically again I come back to the garbage in, garbage out statement, where you need to have a very good understanding of what your material behavior is. If you don't understand what your material behavior is, you will not be able to later predict your defects at all. So what happens in material prediction is basically the availability of the material, and then the test that is associated to that is very, very limited, and then or very expensive if you want to do that. And normally if you don't capture the exact material behavior, the standard thing that normally everyone tries to do is do a tensile test of the specimen, and then take this information coming from the tensile test specimen, like YS, UTS, percentage elongation, anisotropic value. But this is not sufficient for you to do if you are working with a high tensile, with a special material or with advanced materials. So you end up with a wrong prediction of your failure itself. So if you could see here, the failure is at 0 degrees, and then the simulation, what we do by taking into the account of realistic behavior into the simulated value, is giving you a failure at a 45 degrees. So basic test itself is failing, which means if you go forward, you will not be able to exactly correlate your results with the actuals. So the main reason for us to understand the yield locus, yield behavior of your material, if you don't understand it well, you are not doing it right. So what we'd have to do is the traditional approach method. You basically do a tensile test, and then you do a characterization of different material tests like biaxial testing, plane strain test, uniaxial test, shear test. These are the different tests, the input parameters that is required to capture the material behavior exactly, to capture the yield locus exactly. If you don't do that, then there is a simplistic way of actually doing it. ESI, we have developed a formula wherein we will be able to take only the tensile test behavior, initial tensile test behavior, and substitute these values for an algorithm which is basically calculating you the extrapolated values that is coming from different types of tests. And not only that, it also gives you the right material law that needs to be used for this, and also the associated parameters for that. If you have all these informations with you, you will be able to go from a predictive, unrealistic material law to very accurate material law, where you will be able to exactly capture not only the behavior of your material failure, but also the propagation of the crack, etc. So this is actually a very, very starting point for you to get into any of the simulation mode. Now let me get into some of the practical applications. This is a rubber pad forming process, or we call a fluid cell forming process, where there is a tool which is a rigid tool on the bottom. The sheet is put in between a blank holder and then the rigid tool, which is which could be an aluminum, titanium, any kind of sheet. And then you have a flexible membrane on the top, and above the flexible membrane you actually have the vacuum force or the fluid cell force that is coming in. When you're doing that, this is basically to control the spring back that is coming, because when you use a normal punch and tool method, you have an excessive spring back that is coming because of the process itself, which is basically controlled through this, but you still are able to observe amount of spring back that is coming on the component, which is probably not within your particular range. So you basically have to compensate this by changing the tools parameters, by changing the process parameters, etc. And after that you will be able to analyze, rerun the optimization to get it within your your tolerance. Also, some other example is the prediction of your wrinkles and then the cracks, etc. So this is also what you see in reality and what you could see in the simulated one, which is very much matching with your reality. So which means we are talking about a real-time physical, replacing of a physical prototype to the simulated one. Some other process that could be simulated is also the tube forming or tube bending process. If you see here, this is a complete chain where you can take apart, create the complete process design, use a pre-bending approach, do a pre-forming, and then you do a hydroforming process, and then take out the complete part outside by optimizing various parameters. You could see also the rupture risk is calculated based on pressure versus displacement curve, which is a manual fit curve with an automatic solver with which is given from the from the simulation itself. And when you actually run this kind of simulation, you will be able to optimize the parameters well within the simulation itself and go for cutting your tools and then manufacturing it first time right. So one other complex process is the roll forming process, where you will have to actually understand how your flower of your design is going to be when you are rolling it through different rollers. And then you also want to understand how your ends are meeting, because this roll forming tube basically is going through one more set of welding process on the top after the roll forming itself. And then you are supposed to have it within a particular tolerance. The rolls the formed component is going to or is required to be within a particular tolerance. And if you are not within that tolerance, then you are going for a change in the entire process, which is very expensive. The stretch forming process is also one of the typical applications that is normally done in sheet metal in the aerospace industry, where they try to actually see what is to control the spring back, and then the torsional forces as well as the tensile forces that is coming on the actuator and then the component, so that you try to predict the wrinkles and then the spring back as well as the compensation of this particular part. So I was not able to cover all manufacturing process using the sheet metal forming, but we will be fairly able to do any kind of manufacturing process that is there available with different material parameters included for titanium, aluminum, stainless steel, copper, HSS. And if you have specific alloys, as I was telling you, it could be customized for specific alloys by doing basic tensile test parameters and getting into the hybrid lab, material hybrid lab that ESI was talking about before, and then analyze and then implementing the parameters to get out the mechanical behavior that needs to be fed in for the simulation, and then it could be taken further. My next solution is going to be the welding solution, because welding and distortion is one of the important things that needs to be taken care when you're doing the real-time testing. So what do we do in welding challenges? Basically, like the dragging causes of distortion is first the component design, the weld sequence itself, the clamping position, and then the location, the heat source parameters that we are using, and then the material properties. What are the causes of the cracks? Because you have minute cracks or that can be coming, which could be very dangerous in an airline industry or a defense industry. Basically, this is because of the high residual stresses build-up, non-uniform stress distribution, and then the improper phase fraction. So we will be able to simulate everything that is shown in the diagram and in this, and then understand the reason of the failure, and then also to change wherever parameters are required. So when you talk about the welding parameter optimization, it's between the distortion and then the plastic strain. When there is no clamping, you have high distortion. When you have fully clamped part, you have less distortion but high plastic strains, which will lead to the cracks. So you need to understand what is the degree of clamping, and then that's the mission of the welder to optimize these things to reduce the itself. So when we talk about welding, we will be able to do different kinds of weldings. It's single pass, multi-pass welding, friction stir welding, post-heat treatment is also possible, laser welding, electron beam welding, and we will also be able to see the weld grain modeling and then the microstructural analysis of this thing itself. So what are the inputs? Inputs are fairly simple. You have a CAD geometry, material properties, which is derived through some tests, and then you have the clamping conditions, you have the welding locations, and then you have the process conditions. So these are the inputs, and once you have these inputs given, you will be able to take out a temperature profile during the course of welding, and then thermal strains, maximum penetration that is achieved, and also the mechanical behavior including the distortion trend, distortion magnitude, residual stresses, plastic strain buildup, and then the metallurgical data also. I will take a typical problematic case. This is a tube wherein different components are welded together, and then after the welding what was seen is approximately 7 millimeter of distortion. And now let me highlight you a few examples about a few process methodologies that we used to bring down the 7 millimeter distortion to probably a 1.3 to 1.5 millimeter distortion. So if you see here, initially the whole of this part is simulated with different ladder conditions basically. First you have the main tube, and then after that you have the subcomponent welded together, and then after that you are able to achieve or exactly see the problematics that is actually seen in the industry. Once you have the initial conditions simulated, we understood that when we are using 220 joules per minute current voltage heat source, it was giving us the maximum distortion, and then the first thing that we did was optimize the current condition, and then also modify the clamping locations and then the clamping conditions, based on which we were able to actually reduce the amount of spring back from 7 millimeters to say somewhere close to 3.5 millimeters. But still this was not enough. But we also understood that it was actually bending towards one particular direction, and then we found that by pre-bending the tube to a negative bend actually reduces the amount of distortion. So the pre-bending was also simulated using the realistic conditions, and then checking for different kinds of optimization in terms of clamping and welding locations. And finally, from 7 millimeters we were able to bring down the welding distortion to 1.35 millimeters, which was very successfully implemented. So if you talk about the value additions of the simulation itself, we will be able to deal with the realistic tolerance, the material assessment, heat source input parameters, optimized weld plan, clamping conditions, and then the knowledge set can be transferred to other things. Let me move into the next human-centric approach, which is one of the state-of-art virtual reality solution that we have brought in, which is for design reviews, which is for predictive maintenance or whatever you call it, also the maintenance part of it. This runs into a mode of actually like having the design review. Say, assuming it is already an assembled component, the first time is perfectly okay, but when a worker wants to actually disassemble the given assembly, it would be possible for him to do it easily, or we don't know the design approach initially, and then there could be some flexible cables which will automatically have interference, and it would be difficult for the worker to reach out first to the component and then disassemble it. So these are some of the design criteria that you will be able to understand well in advance using the virtual reality solution. The best thing about the virtual reality solution is the physics that is applied to the material itself, including the flexible movement, flexible cables, including the rigid bodies, where we will be able to exactly see the interference patterns. One such also is the landing gear. If you see here, when you see the landing gear, there is a flexible cable which has a particular amount of stretch. If you are not able to exactly predict, either you will be having a less cable length or an additional cable length, which will normally get into the failure mode at later point of time. So we will be able to exactly see this in a virtual reality condition. One other is the accessibility and visibility validation. Say, assuming a worker is standing in a particular position and he wants to actually check what is happening in and around of this, it automatically simulates the pain points in the worker, and then it shows you these are the visibility and accessibility of a particular design, particular structure. It gives you the hotspots of the problems associated to that. Then I was talking about also the resource and tooling verification. Say, assuming you want to see the reachability of a part, be able to do that with the virtual reality solution. So it's just a very realistic tool. If you have the entire design and then you want to check, review, and maintain your entire design, it's possible through the virtual reality solution. I think I'm almost done. Thank you for your attention.